Hello and welcome to this video on thermodynamic properties and the fact that they're all related. At the end of this video you'll be able to explain what fundamental property relations and Maxwell equations are and substitute an equation of state into an equation for du. So where we left off in the previous lecture was with how we can write total differentials for both internal energy and enthalpy. Now what we get is we see that our heat capacity is a useful term in these equations, but we're left with this bit which we don't actually have equations for at the moment because we don't have our u equals and h equals equations that we're able to take the partial differential of. So we need some strategies for getting these bits out of our equations for dH and for du if we want to be able to calculate changes in these variables. Now to kick this off, what we're going to do is we're going to look at what we call fundamental property relations. And so the first of these comes from looking at a closed system, so a fixed amount of stuff, and the first law for that system. So this is something that we've done previously. So the first law for this system is given at the top here, and then if we insert the definition of entropy, then what we're left with is the fundamental property relation between U, S, and V. Now this is the first of our fundamental property relations. To get the one that involves enthalpy, then what we do is we insert this fundamental property relation into our definition of enthalpy. And when we do that, it simplifies down to give us our fundamental property relationship between enthalpy, entropy, and pressure. And so we can continue to do this, so we can get fundamental property relationships for the Helmholtz free energy, and we can get fundamental property relationships for the Gibbs free energy. Now what all these things have in common is that they depend on the first law, they use the definitions of thermodynamic variables, and they're defined by the total derivatives of those variables. Okay, so these are the things that gives us the fundamental property relationship. So they're based on the first law, that is always true, and they're based on the definitions, which are always true, of course, because we made them up. Now, we can use those fundamental property relationships to help us get a little bit further down the road to fixing up those du and dH equations. And so if we go back to our first fundamental property equation, so our du t ds minus p to v, okay, and so whilst we've got this relationship, we also know that the total differential for internal energy has to be equal to our partial differential of internal energy with respect to entropy at constant volume, okay, ds, plus the partial differential of internal energy and with respect to volume at constant entropy, dV. Okay, now if we compare the two equations, what we see is that this term here must equal temperature, and that this term here must equal to negative pressure. And so now we have new equalities that result from the use of the partial differential equations and the fundamental relations. So we can say that, that the partial differential of U with respect to entropy, constant volume, is equal to temperature, and we can say that the partial differential of U with respect to volume at constant entropy is equal to negative pressure. Okay, and so these are important property relations. And so if you went through and did these with the other fundamental properties, then you would get this whole collection of fundamental property relations here. Okay. Now, using these, we can extend them even further using something called Maxwell equations. And so to get our Maxwell equations, what we're using the fact that to take the derivative of something, it's not important in what order you actually take the derivative. Okay, so we can say that du ds, and then with respect to v, is equal to du to v, and then with respect to s. Now, from the previous page, we know that this term here is actually equal to temperature. And then here we know that this term here is actually equal to pressure. And so then we can say that to T to V at constant S and to P ds at constant V are actually equal to each other. Okay, and this is what we call the Maxwell relation. And so when we go through and do this for each of the fundamental property relations, we get the 4 Maxwell equations down the bottom. Okay, and these are useful things for deriving what we're about to derive. But they give you a good idea of how all our thermodynamic properties are all interrelated. And so if you flick open a thermodynamics textbook, what you find is you have all these different relationships that exist. So all this comes from Sandler, I should say. So this setup here are all our thermodynamic properties that we've defined because they're useful: heat capacities, compressibilities, thermal expansion coefficients, so forth and so on. Then we have our Maxwell relations, and then also our thermodynamic identities. Okay, and so we just derived all these. These are very useful. And then we can use them to derive larger equations that are actually useful for us. And so we'll actually be deriving this equation in just a moment with the help of those previous ones. And then Sandler decided that these ones were useful as well. Okay, so there are thousands of property relationships. They're all related to each other. It's like digging up a gigantic family tree. If you dig back far enough, you're bound to find that they're related in some way. Now, if we want to calculate changes in U, okay, so we remember back when we said, okay, the total differential of U is this equation up the top here. Okay, and so we can get one bit of it by using the definition of the heat capacity, but this is where we were stuck. Okay, we didn't know how to do this part. And so what we can do is we can then use our fundamental property relationship. Okay, so we're replacing U with T delta S P delta V, and then we can expand that out. Okay, so we've got pressure now. Okay, that's good. We've got equations for pressure with the equations of state, but we're still left with this term here. So how do we get rid of that? Our next step is to use a Maxwell property relation. And so now we can see actually something very useful. So now we've, instead of an S and a V, we've got a pressure term in here. Okay, and a pressure term is good because we have equations of state. When we substitute these things all in, what we're left with is this equation for the total differential of U. And this is very useful because we've got heat capacity and then a term that changes with pressure, and then our other term is just the pressure. Okay, we can get all these things. Okay, so we can get them all from our equation of state. Okay, and then if we want to calculate a change in U, then we just need to integrate these parts. Okay, so we're just integrating this term over here. Okay, so now that we've got an equation that calculates the change in internal energy using the equation of state, we can now use this to calculate the departure internal energy. And so we start with the definition of the departure function, that the internal energy is made up of the ideal gas part of the internal energy plus the departure component of the internal energy. This then gives us the definition of the departure function. Okay, so and now we're going to look at how we calculate this using the equation of state. So to do this, we'll consider first of all the ideal gas part. So when do we expect an ideal gas condition to happen? So of course at low pressure. So we can take the very extreme case of saying, okay, if the pressure was equal to 0, and if the volume then in that case would be infinite, these conditions then give us the ideal gas internal energy. Now, to get the actual internal energy, or the difference between the ideal gas and the real internal energy, we're then interested in the difference between these ideal gas conditions and the internal energy when we actually have the real volume at the temperature and pressure that we're interested in. So using the equation from the previous slide, where we can simply ignore the temperature contribution to this, and so then we're just using this part of the equation. So when we go back over here, we can see that the departure enthalpy is the integral of that term, integrating from infinite volume, where it's an ideal gas, up to the actual volume that we're interested in. And these terms in the equation here, so T is the temperature that we're interested in, okay, but then these other two terms are from the equation of state. So if we take the van der Waals equation of state as an example, then we're substituting in that the pressure is equal to RT on V minus B minus A on V squared. Okay, so this P here is not a number, okay, it's an equation, so that's where we substitute in the equation of state. And then there's partial differential, okay, so if we take the partial differential of the pressure for the equation of state, then what we're left with is R on V minus B. So to recap what we've done in today's video, so all thermodynamic properties are related to each other in one way or another. Because of this, it's possible then to derive relationships from the first law, thermodynamic definitions, and partial differential equations. It's these relationships then that allow us to calculate things like changes in internal energy from an equation of state. This then means it's possible to derive an equation for changes in U that uses just the heat capacity and the equation of state. And then this means that we're able to calculate the departure internal energy using an equation of state, which is going to be very handy for stuff that we're doing later on. Okay, so thanks a lot for listening, and I'll see you next video.